What is dark matter, and why is it essential for understanding the universe? This is one of the central questions of modern cosmology. Dark matter is a mysterious form of matter that neither emits, absorbs, nor reflects light, which makes it impossible to observe directly. However, it has a real gravitational influence on surrounding matter and light, and it is precisely this influence that has allowed scientists to conclude that it exists. There is much more dark matter in the universe than ordinary atomic matter. It forms the gravitational skeleton upon which galaxies and galaxy clusters are built. Although we do not yet know what dark matter is composed of and haven't detected its particles, we can see that its role in the universe's development is extremely important. That's why in this video, we're going to explore the most popular facts about dark matter. So let's figure this out together. One of the most mysterious properties of dark matter is that it doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation. This means that it's completely invisible to our telescopes, regardless of the range they operate in: optical, X-ray, infrared, or radio. In everyday life, we see objects thanks to light. For example, the sun emits light, which reflects off objects and reaches our eyes. Even a non-luminous body like the moon is visible because it reflects sunlight. Light interacts with atoms, electrons, and other charged particles in matter. This is the basis of electromagnetic interaction. Dark matter, on the other hand, does not participate in electromagnetic interactions. It is transparent to light. Photons, particles of light, do not notice it, and vice versa. That's why we cannot see it. It doesn't produce any signals that could be detected even by the most sensitive telescopes. This property makes dark matter extremely difficult to study. Scientists can only indirectly infer its existence by observing how it gravitationally affects the surrounding universe. Indirect evidence of its existence has been accumulating for decades, from observing the motion of galaxies within clusters to gravitational lensing, when massive objects bend the path of light from distant galaxies. And in all cases, we see the same thing. The universe contains much more mass than we can observe. Due to its invisibility, dark matter got its name. Not dark, as in color, but because it is hidden from our sight. It is a shadowy component of the universe, present everywhere, yet it doesn't shine, twinkle, or leave a light trail. Even though dark matter is invisible and doesn't interact with light, it has one fundamental property. It has mass and therefore creates gravity. It is thanks to this gravitational influence that scientists first suspected its existence and continue to study its nature. One of the first to notice unusual gravitational effects was the Swiss astronomer Fritz Zwicky in the 1930s. He studied the motion of galaxies in the Coma cluster and noticed that the galaxies there were moving too fast. If we account only for the mass of visible stars and gas, their gravity would be too weak to hold the cluster together. The galaxies should be flying apart. But they weren't. Zwicky proposed that there must be some invisible mass, which he called dark matter. Later, in the 1970s, astronomer Vera Rubin and her colleagues conducted a more significant study. They measured the speed at which stars rotate around the centers of spiral galaxies. According to Newton's laws, the farther a star is from the galactic center, the slower it should rotate. Just like planets in the solar system, Mercury orbits quickly, while Neptune moves slowly. But in the case of galaxies, stars were rotating too fast, and the speed didn't decrease with distance as it should have. This phenomenon became known as the flat rotation curve. It indicated that there must be a massive halo of invisible matter surrounding the visible galaxy, whose gravity pulls on the stars, causing them to move faster than visible matter alone would allow. That mass is dark matter. In addition, dark matter is detected thanks to a phenomenon predicted by Einstein's general theory of relativity, gravitational lensing. If a massive object lies between us and a distant source of light, such as a galaxy or quasar, its gravity bends space, and the light changes direction, as if passing through a lens. The greater the object's mass, the stronger the distortion. By observing such lenses, astronomers can calculate the mass of the lensing object. Often it turns out that the distortion is far greater than what can be explained by visible matter alone. This means that a significant portion of the mass causing the gravitational effect is invisible. Once again, that's dark matter. The gravitational influence of dark matter was also crucial in the early universe. When the universe was still very young, hot, and homogeneous, even small clumps of dark matter attracted ordinary matter, gas, forming clots, from which stars, galaxies, and galaxy clusters later formed. Without dark matter, the structure of the universe as we see it today could not have formed so quickly. This is confirmed by cosmic observations, including data from the cosmic microwave background, such as from the Planck telescope. One of the most astonishing facts about the universe is that the vast majority of its matter is invisible. According to current understanding, dark matter accounts for approximately 5 times more mass than ordinary matter. In other words, everything we see around us, stars, planets, gas nebulae, galaxies, intergalactic gas, accounts for only about 5% of the universe's total composition. The rest is invisible mass. About 23% is dark matter, and the even more mysterious dark energy, about 72%. Dark matter has an entirely different nature. It only interacts gravitationally. It does not emit, absorb, or scatter light, electromagnetic radiation, does not participate in nuclear or electromagnetic interactions, is not made of atoms. Otherwise, we would detect it in spectra, thermal background, or the cosmic microwave background. Behaves as a cold and inert form of matter that does not form compact structures on small scales. For example, it doesn't form stars. If dark matter were made of atoms, it could glow or at least affect light. It would form compact objects, stars, planets, gas clouds. We would detect it with telescopes or in radio observations. But none of that is true. Dark matter is transparent, does not form small structures, and doesn't participate in chemistry. In the early stages, there were hypotheses that dark matter might consist of ordinary matter we simply can't see, such as cold brown dwarfs, invisible black holes, or planets. These objects were called MACHOs, massive compact halo objects. However, gravitational microlensing has shown that there aren't enough of these objects in the galaxy to explain all the dark matter. So what is this substance? Dark matter is non-baryonic matter, likely made up of yet unknown elementary particles that have no electric charge, very rarely interact with other particles, may be stable and massive. Some of the most popular candidates for dark matter particles are WIMPs, weakly interacting massive particles, and axions, hypothetical light particles or sterile neutrinos. Dark matter remains one of the greatest mysteries in modern science. Although we cannot observe it directly, numerous indirect pieces of evidence, from galaxy rotation curves to gravitational lensing and the structure of the cosmic microwave background, testify to its real existence and vital role in the formation and evolution of the universe. At the same time, due to the lack of direct detection of dark matter particles, scientists are also exploring alternative theories of gravity that might explain observed phenomena without invoking dark matter. We'll talk about those next time. And that's all for now. Keep searching for dark matter.